topic of imperfection in solids, popularly known as defects in crystalline solids. This topic is very important from both entrance exam perspective as well as board exam perspective. So, when you talk about imperfection or you talk about defects, they are of two types. First type, point defects. Right from the name, point defect, that means a lattice point is missing or lattice point is added. The next one is called as line defects. From the name, line defect, that means the entire line of lattice point is added or entire line of lattice points is missing. Our main syllabus is based only on point defects. So, everything right beyond this will be based only on point defects, and our curriculum does not involve line defects. So, after this we will never learn anything about line defects. Everything will be about point defects. So, when you talk about point defects, there are further types. First type, vacancy defect. From the name, you can clearly observe your lattice points are missing. What was expected here? Expected was a sphere. What was expected here? Sphere. But that is missing. So, lattice point is missing. If it is missing, then such a type of defect is called as vacancy defect. Here atoms or ions are missing for whatsoever reason. The next part of a defect is interstitial defect. The name itself clearly indicates interstitial. That means there is lattice points are added. So, this lattice point and this lattice point is extra added to our crystalline solid. Therefore, it is an example of interstitial defect. That means here atoms or ions are added extra. Now, when you talk about ionic solid, which is the main part, henceforth has more complex defects than the simple defects of vacancy and interstitial defects. Remember, ionic solids will be more complicated, defects will be present. Second classification, point defects are also classified into three types. The first type, stoichiometric defect. The name itself indicates stoichiometric. That means there is no change in the chemical formula and the stoichiometry remains same. That means chemical formula remains same. Here, for ionic solids, there will be, if the chemical formula has X cations and Y anions, again the ratio of the cations and anions at the end of this defect will be the same. There are two particular and very popular defects under stoichiometric defects, Schottky defect and Frenkel defect, which are popularly found in ionic solids. The next category of defect is impurity defect. The name itself indicates impurity is added by human beings. So, these defects are due to addition of foreign substance, that can be either atom or it can be an ion. Impurity defects are of further types: substitutional impurity defect and interstitial impurity defects. Many times name tell you more about the defect itself. The third and the last category of point defect is non-stoichiometric defect. The name itself indicates the ratio of cation and anion before and after this defect does not remains same. That means there is a change in the chemical formula. So, ratio of the number of cations and anions may not be a whole number. Such a type of defect is called as non-stoichiometric defects. There are also further types: metal deficiency defect and metal excess defect. So, the second classification of point defect is much more important for our syllabus perspective. So, you should have learned it here. Point defects are of three types: stoichiometric defects, impurity defect and non-stoichiometric defects. We come to the first type, stoichiometric defects. In stoichiometric defects, there is no disturbance to the stoichiometry of the solid. That means chemical formula of the compound at the end of this defect remains same. They are of further types: vacancy defect or self-interstitial defects, more popularly found in molecular solids, not discussed in detail in our syllabus. Schottky defect and Frenkel defect found in ionic solids and discussed in too much detail in our syllabus. They are also called as intrinsic and thermodynamic defects. They got this name because it is found during crystallization, or it is found during heating or hammering or such thing which are heat related. Therefore, the name thermodynamic defects. Most important of all this defect is Schottky defect and Frenkel defect. So, we come to the first one, stoichiometry defect. Under that, Schottky defect. What you are able to see in this place, we were expected to have Cl minus. In this place, we are expected to have Na plus. How you came to know that there should be Na plus only here? Because any cation is surrounded by anion. Anion is bigger and shown here by blue colored sphere. How you came to know here Cl minus is present? Because it is surrounded by cation, and cations are comparatively smaller. What you are able to see in this diagram, that anion and cation both are missing. If equal number of cations and anions are missing, then such a defect is called as Schottky defect. It is also known as cation anions vacancy defect or simply vacancy defect. Now, when is this Schottky defect happens? It happens during crystallization. Right, when crystallization happens faster, some of the cations and anions cannot take their place. You can imagine mass PT in our school. During mass PT, some of the students purposely fall sick and they don't come in their positions, right, in mass PT, physical training session. So their positions in mass PT are vacant. That's for us to understand Schottky defect. So for us, Schottky defect is that defect found in ionic solids where cations and anions are missing and they are equal in number, and this usually happens during crystallization. Now, Schottky defect, what are the conditions for successful Schottky defect? These are favorable conditions of Schottky defect, but Schottky defect can happen otherwise also. So, most favorable conditions of Schottky defect, if you know Schottky defect, the cation anion is missing. So, most favorable condition of Schottky defect is there should be a high degree of ionic character, and you are aware high degree of ionic character will be found when group 1 and group 17 elements will come together. Group 1, group 17, that means alkali halides, right? They will have sufficient high degree of ionic character and they should have high coordination number. High coordination number, that means cation should be surrounded by large number of anions, or anion should be surrounded by large number of cations, and this happens when the radius ratio is very high. Example where radius ratio was very high and almost close to 1, cesium chloride. If you remember, in cesium chloride radius ratio was greater than 0.732. That means it was almost close to 1. Then stoichiometric defect, Schottky defect. What are the consequences of Schottky defect? You should remember, in Schottky defect, cation and anions are missing. Naturally, if cations and anions don't reach their place, density of this ionic solid will be lesser. So, decrease in density. Because equal number of cations and anions are missing, electrical neutrality of a unit cell or a crystalline solid is preserved. That means the net charge on the ionic solid is 0. So, consequence of Schottky defect, density decreases and the net charge remains the same, 0. If you check the example, you will realize NaCl, KCl, cesium chloride, KBr, most of this example are alkali metal halides. But one is odd man out here. Silver bromide is also found to be an example of Schottky defect. For us, this is an unusual, exceptional example to remember. Silver bromide is an example of Schottky defect. if you try to understand Schottky defect, are you able to see the right ions are missing, they are unoccupied, that means lattice vacancy is created. So a positive ion is missing, negative ion is missing, so overall electrical neutrality is maintained in Schottky defect. In Schottky defect, cation and anions are not able to reach their positions during crystallization. One of the best example for Schottky defect is NaCl. We go to the next stoichiometric defect, not next. Alright, one experimental data available of Schottky defect. Factual experimental data available of Schottky defect. This is an NCERT diagram. Those who want to know, NCERT diagram of Schottky defect is like this, where you are able to see a square has been shown. That means here cation is missing. A square has been shown. Here also cation is missing. A square here is shown. That means anion is missing. And one more square has been shown. That means anion is missing. So as per NCERT diagram, they are still showing that the cation and anions are missing. The factual data which is available is, if you take 1 centimeter cube volume of NaCl crystal, experimentally it is found 10 to the power 22 right ions are present, combined of cations and anions. Out of this, it has been found 10 to the power 6 Schottky pairs are missing. 10 to the power 6 Schottky pairs are missing. That means there is one Schottky pair right in 10 to the power 16, because we got 10 to the power 22 minus 10 to the power 6, that is 10 to the power 16 ions. Right, one Schottky defect is found. That's experimental data for us. That means quite sufficient number of Schottky defect is found in our experimental data. So that was all about Schottky defect. Right, if you want, you can again see this video, understand it well before moving further. So we come to the next part of stoichiometric defect, Frenkel defect. We have just completed our learning of Schottky defect. Now we are coming to Frenkel defect. Frenkel defect, right, the best example are like silver chloride. In silver chloride, silver ion, which is a smaller ion, slips and goes to another position, causing accumulation of cations at one place, causing accumulation of anions at other place. The diagram that we saw with NaCl was not the best example. The best example is silver chloride, where silver, by virtue of its smaller cationic size, slips and occupies an interstitial space. Frenkel defect is found when cation, which is a smaller ion, is missing from regular latticeoid and occupies the interstitial void between lattice point. It is also known as dislocation defect. It is an example of vacancy at one place and interstitial position occupied at the other place. So it is a combination of vacancy and interstitial defect. That's the next question that we have is, when will you have Frenkel defect? This usually happens when an ionic solid or a crystalline solid is heated, then cation has certain amount of mobility and loses its site and goes to interstitial place, or when you hammer it or you hit a right ionic solid very hard, then cation gets an opportunity to slip from its position and go to interstitial void. That was about Frenkel defect. So Frenkel defect means cation right goes from its lattice point to interstitial space. You can remember the word फिसलना, फिसलना, Hindi word फिसलना, and Frenkel defect. This is how you can remember. We would like to understand more about Frenkel defect. Example, if you remember, example is AgCl, silver chloride, where silver ions goes from its lattice point to an additional point, causing accumulation of cations at one place and keeping anions also accumulated at another place. What is the condition for Frenkel defect? It will happen when there is a large difference between cation and anion. That means cation is much smaller as compared to anion. So naturally, if you find out radius ratio, it will be very small. So when radius ratio is very small, that means when cations are much smaller than anions, such type of defect, right, will have more chances. So these are all favorable conditions of Frenkel defect. When this happens, when radius ratio is very small, that means coordination number is low. Example, zinc sulfide, if you remember, where coordination number of zinc was 4. Coming to the next one, Frenkel defect, consequences of Frenkel defect. This is one more diagram for us to know. The cation, if you are able to see, has shifted its position from here to here. So that's Frenkel defect. What happens to density? It remains same because in a unit cell, number of cations and anions are remaining same. Only dielectric constant increases, because at one place cations are getting accumulated, at other place anions remain more in number. So it causes polarization of an ionic solid, which in physics is reflected as a dielectric constant will be more. If you see more example, they are transition metal salts. Transition metal salts, for us this is an odd man out, but most of the examples are transition metal salts is an example of Frenkel defect. Remember Frenkel, F फिसलना, cation अपने जगह से फिसल जाता है. Right, what is unusual for us to know? As per NCERT, silver bromide is an example given for both Schottky and Frenkel defect in NCERT textbook. Here is an example of Frenkel defect. So if you see Frenkel defect, what you realize? This is an ionic solid. Now, which type of an ionic solid are you talking about? You're talking about a transition metal ionic solid, which is made up of cations and anions. A cation, being smaller in size, slips from its position and occupies interstitial right space, and this causes accumulation of cations at one place and anions are left behind at the other place. So that was about Frenkel defect. Right, this is an example for us to understand Frenkel defect and Schottky defect at one place. In Schottky, cations and anions both are missing. More often it happens during crystallization, when cations and anions are not able to reach their position. In Frenkel defect, cation from its original position slips, creating a vacancy at one place and occupying interstitial site at other place, creating a vacancy at one place and occupying interstitial site at the other place. So Frenkel defect, we remember फिसलना. So cation अपने जगह से फिसल जाता है और interstitial site में आ जाता है. Those who still want to understand, imagine the entire room is filled with footballs, big size footballs. Imagine entire packed, full packed with footballs. No space for no more football to be added. Now imagine you try to put a tennis ball into the same room which was filled with footballs. You can still put tennis balls. But where tennis balls will go? Tennis balls will slip all different positions and will go into a void, different sides of void. That's another way of imagining Frenkel defect. Coming to more discussion, comparison between Schottky and Frenkel defect. Now, Schottky defect. You should always remember in Schottky defect what happens. Cations and anions are not able to reach their positions. While in Frenkel defect, what you should remember? Cation slips. So, Schottky defect will happen when there is a large difference in cation and anion. You can imagine, right, anions are present during crystallization and cation is unable to come in that place, right. It was trying to come, right, maybe after certain time period, but is not able to come because cation is also larger in the size. Because of the almost equal size of cation and anion, once anion has got place, cation cannot. Similarly, when cations have occupied that position during crystallization, anion also is larger, cannot slip through. Schottky defect happens when cations and anions are almost of similar size. That means difference in cation and anion size is small. In Frenkel defect, cation is much smaller, therefore cation slips. So, difference between cation and anion is large. Both cation and anion are missing or they leave their lattice points. Here, cation leaves the lattice points and occupies interstitial position. This is an example of vacancy defect, while Frenkel is an example of both vacancy and interstitial defect. In Schottky, density gets reduced. In Frenkel, there is no change in density. In Schottky, the examples are alkali metal salts, exceptional for us to remember AgBr. In Frenkel defect, examples are transition metal salts of group 17 and 16. Right, for us, just important point to remember, AgBr at both the places as per NCERT textbook. So, that was comparison of Frenkel and Schottky defect at one place. Student friends, we come to second type of defects under the category of point defects. We have already learned under point defect stoichiometry defects. Now, we come to the second category called as impurity defect. From the name, it's clear, impurity. Impurity, that means a foreign atom or an ion is added, right, which is different than host atoms or ions. Then such a type of defect is called as impurity defect. Remember, foreign atoms or ions which is different than host atoms or ions is added. It is of further type: substitutional impurity defect and interstitial impurity defect. In substitutional impurity defect, as per the name, a foreign atom or a species will occupy the lattice points. So, in the place of host atoms, now a foreign atom or an ion will occupy a position. Interstitial, right, impurity defect is that in which the foreign atom will occupy interstitial sites, or you can call them as voids. So, here foreign atoms or species will occupy voids. Right, under that impurity defect, we come to first one, substitutional impurity defect. The name clearly indicates substitutional, that means it replaces host position or lattice points by foreign atoms or ions. So, remember, foreign atoms or ions are present at lattice sites in place of host atoms or ions. Example is alloy. If you take an example of an alloy, one of the very popular alloy made up of zinc and copper, that is brass, then you should remember brass is made up of base metal as copper. Base metal is copper, to that zinc is added. Now, whatever zinc is added, zinc will take the position of copper. This was previously filled by copper, now is occupied by zinc. This position was also previously filled by copper, now it is filled by zinc. That means zinc takes the position of host copper atom. Such type of defect is called as substitutional impurity defect. The question is, why zinc occupies the position of copper? Because size of zinc and copper is almost same. You already know atomic number of copper 29, atomic number of zinc 30. So, they are next to each other. So, their sizes are almost same. So, zinc cannot accommodate itself in void, so it will take the position of copper. So, this is an example of substitutional impurity defect, where zinc substitutes copper host atoms position. We go to the another category example of substitutional impurity defect, that is vacancy created through aliovalent impurity. Now, the word aliovalent is introduced for the first time. When you say the word aliovalent, that means the ion which is added has oxidation number different than the host ions. Aliovalent means it is having oxidation state different than host ions. In this case, the ion added has oxidation state greater than the host ions. Right, if you see an example, imagine, right, entire thing is filled by NaCl. Your crystal lattice is NaCl. You know, in crystal lattice of NaCl, Na plus is surrounded by Cl minus and Cl minus is surrounded by Na plus. Now, imagine this is a case. Now, to this you add strontium chloride. When you add strontium chloride, you have added two ions, strontium and chloride ions. Now, chloride is already a host ion. So, what is a foreign ion that you have added? Strontium. Now, strontium has a charge of 2 plus. Now, to maintain electrical neutrality, one strontium ion, when it enters into a crystal lattice of sodium ion, during crystallization, we have added strontium chloride during crystallization of NaCl. So, strontium now comes under the OR along with the crystal of NaCl. So, one strontium displaces two sodium ions to maintain electrical neutrality of crystal lattice, of which one sodium ion's position is filled by strontium and other sodium ion's position remains empty. You can clearly observe this was a position of Na plus, this was also a position of Na plus, both the positions were of Na plus, but you are able to find there is only one strontium ion, because one strontium ion can remove two Na plus from the system. One position it occupies and other position it keeps vacant. So, there will be a vacancy created. What is important is strontium takes the position of sodium ion. Therefore, it is an example of substitutional impurity defect, but it creates vacancy in turn. Now, imagine in place of strontium, if you had aluminium ions, then aluminium ions would have displaced three sodium ions. Three sodium ions would have displayed, of which one position would have been occupied by aluminium and two vacancy would have been created if instead of strontium we would have used aluminium ions. But the example which is available in NCERT textbook and in our board textbook is of strontium chloride added to NaCl. So, in order to maintain electrical neutrality of a crystal lattice, every strontium ion removes two sodium ions or does not allow two sodium ions to come into crystal lattice, of which one place is occupied by strontium ion and the other place of sodium ion remains vacant. So, it creates vacancy. So, vacancy created through aliovalent impurity. This. So, that was about substitutional impurity defect. Second example. First example was brass. Second example is strontium chloride added during crystallization of NaCl. We go to impurity defect, the next category. The next category is interstitial impurity defect. The name itself indicates that the foreign atom or a impurity atom occupies interstitial space. Other word for interstitial space, voids. It occupies voids. Example, stainless steel. If you see stainless steel, it is made up of iron, which belongs to 4th period and is also containing carbon which belongs to 2nd period. We know their sizes differ a lot, of which iron is a bigger atom, carbon is a smaller atom. Because the difference in the size is very large, carbon will occupy the void. That means in a 4th period element, if you add 2nd period element, there is a possibility of interstitial impurity defect. So, example, steel, in which when you add carbon to a space of iron atoms, then carbon will occupy interstitial space only because carbon atoms are small in size. So, they will occupy the space of voids, they cannot displace iron atoms. So, this is a last example under the category of impurity defect, interstitial impurity defect. Next part of point defects, that is non-stoichiometry defects. The third category under point defect is non-stoichiometric defects. These defects disturb the stoichiometry of the solid. What does that mean? The chemical formula will undergo a change. So, if a chemical formula undergoes a change, either there may be more cation or there may be more anion. So, stoichiometry will get disturbed. It is of further two types. Metal excess defect, from the name it is clear that cations will be extra, and metal deficiency defect. In this, metal ions will be less, that means anions will be more. Metal excess defect. In this defect, metal cations are more than the number of anions. When metal cations are more, such a defect is called as metal excess defect. It is due to anionic vacancies or it can be due to extra cations. So, we come to metal excess defect under the category of non-stoichiometric defects. If anion is missing from its lattice side, leaving behind the electron, so that the charge remains balanced, then such a type of defect is called as metal excess defect. Anion will be missing from the lattice side, leaving behind the electron, or electron will occupy the position of an anion. Example is this one. Are you able to see a diagram that electron is at the place of anion? Electron is left behind at the place of anion. That means anion for us is somewhat lesser. Metal excess defect. Site containing this electron are called as F center, because they are responsible for imparting color to a crystal. What does F stands for? F is a German word which stands for Farbenzenter, indicating it is a center or a site responsible for color. Now, this is called as anionic vacancy. So, under non-stoichiometric defect, metal excess defect, this is due to anionic vacancies. Now, this is vacancy. So, vacancy is a speciality of Schottky defect. So, these examples are found in Schottky defect crystal lattice like NaCl and KCl. There this examples exists. So, imagine if it is NaCl, then Na plus will be extra and Cl will be lesser. So, are you able to see the stoichiometry of NaCl, which was Na1, Cl1 is now not applicable, and therefore, it has become non-stoichiometric. So, we have just learned non-stoichiometric defect, metal excess defect due to anionic vacancy. More about this we are going to learn it now. So, non-stoichiometric defect, metal excess defect, these are experimental facts. We all are aware that NaCl, KCl, lithium chloride are colorless, or you can say white solid, as they have no unpaired electron which can be excited by visible light. Now, any substance where unpaired electrons are present or where electrons are easy to excite, they absorb visible light. Any substance which has unpaired electrons or electrons which are easy to excite, then such type of species absorb visible light. When they absorb visible light, such type of species become colored. But we are aware, if you take an example of NaCl, then this is like a neon and this is like a argon. So, they do not have unpaired electron or electron easy to excite. Therefore, always NaCl, KCl, lithium chloride crystals are always colorless, or you see them white. But it is found when sodium vapors are passed over sodium chloride. When sodium vapors are passed over sodium chloride, it is found that sodium chloride turns yellow in color. Similarly, when potassium vapors are passed over potassium chloride, it turns lilac or purple in color. Similarly, when lithium vapors are passed over lithium chloride, it turns pink in color. Now, these are experimental facts. Now, for us it is unusual because we never expect NaCl, KCl and lithium chloride, which are otherwise white salts, to become colored. Why they became colored? This is what is our query. So, to solve that query, we will try to understand this example. Imagine there was Cl minus at that place only. Imagine Cl minus is there. When sodium vapor comes and condenses. Now, imagine sodium vapor means sodium atom. Sodium atom has come and condensed on sodium chloride crystal. As soon as sodium atom comes here and condenses, you should know when sodium vapors have come, that means they were hot. That means they were at high temperature. We are aware sodium has low ionization enthalpy. That means it can easily lose an electron. So, sodium atom which has got condensed on sodium chloride becomes immediately positively charged and loses its electron. The Cl minus which was at the surface, right, loses its position and comes here so as to develop more electrostatic forces. So, the Cl minus which I am shading it out has shifted its position and has gone here. Then the chloride ion which was present here comes here and takes the position of the previous chloride ion, and this becomes vacant. This vacant chloride ion's position is taken by this chloride ion and this position becomes vacant. In this vacant position, the electron which was lost comes here and takes this position. But why electron has to come here? So as to develop electrostatic force of attraction between an electron and nearby cation. Otherwise, if the electron doesn't comes, cation will have repulsive forces. So, what you realize, Cl minus which was at this original position has got shifted up, and that position has been taken up by the electron which has been lost by sodium. So, can I say there is an extra electron present at this? Now, this electron is easy to excite. When it is easy to excite, because it is loosely bound, the substance as a whole will absorb visible light and will become colored. So, now you understood why when sodium vapors are passed over sodium chloride, why sodium chloride turns yellow, because of that electron, right, which has got trapped. This electron is not tightly bound, it is loosely bound and therefore easy to excite. So, that is the reason why when sodium vapors are passed over sodium chloride, it turns yellow. When potassium vapors are passed over potassium chloride, it turns lilac or purple, and when lithium vapors are passed over lithium chloride, it turns pink. If you want to know this, right, colors are also the flame colors. When sodium vapors are heated in a flame, right? It gives yellow color to that Bunsen flame. When potassium salts are heated in flame, blue colored Bunsen flame, you get lilac or purple color. When lithium vapors or lithium salts are heated in Bunsen flame, they give you the typical pink color. So that color is due to this extra electron trap. So in German language it is called as Farben-Center. Farben means color, center means center, center for color. So this type of metal excess defect is responsible for color and therefore popularly called as F-center defects. In this, can I say sodium ions and chloride ions which were in the ratio of 1:1 will not remain as 1:1, there will be extra sodium ions. In diagram we had shown only one sodium atom, but in real practice there will be many such sodium atoms condensing at different places of sodium chloride. That means sodium will be extra in number, that means metal is excess, therefore it got the name as metal excess defect. Are you able to see the stoichiometry or the chemical formula has undergone a change? Because chemical formula has undergone a change, it comes under the category of non-stoichiometric defect. So why sodium chloride turns yellow when sodium vapors are passed? Answer is F-center defect. Why potassium chloride turns lilac or purple when potassium vapors are passed? Because of F-center defect or metal excess defect. That's the answer for us. After this, we go to next non-stoichiometric defect, metal excess defect. We are still there. We are all knowing zinc oxide, which also doesn't has any unpaired electrons because Zn2 plus is 3d10. It has no unpaired electrons. Therefore, zinc oxide is white in color at room temperature. So this is how zinc oxide is there. Zinc ions are surrounded by oxide ions from all the sides, and oxide ions are surrounded by smaller zinc ions from all the sides. This is what is your zinc oxide structure. Before heating, zinc oxide is found to be white colored solid, but as soon as you subject zinc oxide to a flame or you heat it, it turns yellow as shown in the diagram. What exactly happened? Why it has changed yellow in color? The answer available is zinc oxide on heating. Zinc ions get separated, oxide ions get separated, but oxide ions decompose to give you oxygen gas and electrons are left behind. So oxygen which was present here has got converted to O2 and has gone out in the air as oxygen gas, and the oxide ions electrons are left at the site of oxide ions. So electrons are left at the site. Because of this extra electron, now it is easy to excite such an electron. Therefore, now it will absorb visible light and will become colored, and that color is yellow color. And what has happened? Because zinc oxide has decomposed, anion has gone out and cation has been left behind in the lattice. Zinc doesn't goes out, zinc remains there. Only oxide ions gets converted to oxygen gas, leaving behind electrons. So can I say cations have become extra? So we say extra cations. So this is metal excess defect. So zinc oxide, which was in the formula of zinc 1 oxygen 1, now what has happened? Zinc has become extra, oxide has remained lesser. So we show zinc has become extra, so it has become non-stoichiometric defect. Extra cations which are there, they also can shift to that interstitial sites now because there is an empty space created. So it is found many a times this extra cations may occupy interstitial site, and electron can occupy interstitial site or they can occupy empty lattice site. When I say wherever oxygen is there or oxide ion is there, can I say it is a lattice site? So, electron can be present in the lattice site or electron can slip and go into interstitial site. So, it is one more example of metal excess defect. This also can be called as F center defect because that extra electron is responsible for color which was otherwise absent. Since interstitial site is occupied by an ion, so this defect is found in crystals like Frenkel defect. You remember in Frenkel defect, Fiselna cation was getting slipped. So, here also cation is almost getting slipped. So, Fringle defect examples and metal excess defect example with extra cations are of similar type. Example, zinc oxide. This is an experiment that we are going to learn where we are going to understand non-stoichiometry defect, metal excess defect due to extra cation. If you check, before heating, zinc oxide is white in color, but as soon as you subject it to a flame, as soon as you subject zinc oxide to a flame, what you will observe? That zinc oxide, which is white colored solid, now will have yellow color tinge, and you all know that why this is yellow colored, because of that extra electron left and oxide ions are destroyed into oxygen, leaving behind an electron. So, now you understood, after heating it has become yellow colored solid, and the reason is oxide ion has got decomposed as oxygen and the electron has been lost, leaving behind electrons. We go to next category, non-stoichiometric defect due to metal deficiency. Now, in real life, experimentally it has been found, if you find out experimentally FeO, then FeO does not has a formula of Fe1 and oxygen 1. Instead, it has unusual formula of Fe.93 or Fe.96 and oxygen 1. That's unusual. If I consider oxygen as 100, then Fe is 93. If you consider as oxygen 100 or oxide ions as 100, Fe is 96. So, can I say metal is less? Therefore, this defect got the name as metal deficiency defect. Now, we have a question in our mind, why this unusual formula? What is the reason? And the reason is that some ferrous ions by air gets converted to ferric ions. So, ferrous oxide solid, when exposed to air, some ferrous ions get converted to ferric ions. That means, in ferrous oxide solid, we have ferrous ions as well as ferric ions along with oxide ions, ferrous as well as ferric ions. Both these ions are cancelling the charge on oxide ions. Because of this unusual formula exists. Such a type of defect is called as metal deficiency defect. To understand this better, we will try to do a numerical. Find percentage of ferrous ions in Fe.93 oxygen. This numerical has been already asked in JEE main examination. Let the number of oxide ions be 100. Then what will be the number of Fe ions? 93. But you are knowing that Fe ions here are ferrous as well as ferric. Let ferrous ions be X. Therefore, ferric ions will be 93 minus X. Now, we are aware for any crystal lattice, for charge neutrality, total positive charge and total negative charge is 0. Positive charge is due to ferrous ions and ferric ions, and negative charge is due to oxide ions. Now, each ferrous ions has a charge of plus 2. So, X ferrous ions will have a charge of 2x. Every ferric ions has a charge of plus 3. So, 93 minus X plus 3 charge, total charge on ferric ions will be 93 minus X. That is the number of ferric ions, and the charge on ferric ions is 3. Number of oxide ions are 100, charge on each oxide ion is minus 2. All charges put together will be 0. If you solve this algebra, the next value will be 79, and somebody solves this, it will be 14. Are you able to see 79 ferrous ions with a charge of plus 2 and 14 ferric ions with a charge of plus 3, total have a charge of plus 200. 100 oxide ions with a charge of minus 2 have a charge of minus 200. So, total charge is 0. Therefore, this unusual formula is there. So, if you calculate number of ferrous ions are 79 out of total Fe ions 93. We know if you use small algebra, the answer has to be more than 79. If you use a calculator, approximately the answer is 85%. Now, you realize why the formula is unusual, because the total charge is 0, but the total charge 0 is not made alone by ferrous ions, but it is also done by ferric ions. So, that was about the last part of non-stoichiometric defect called as metal deficiency defect, and this numerical helps us to understand why it happens so. Now, this happens in other types of solids also, like solids of nickel. For nickel solids also it can happen because of variable valencies of nickel found in the nature. So, it can happen in other types of examples too. We come to solid state topic, electrical properties. Now, solids are of various types. They are conductors. You are already aware various metals around are conductors. Wood, plastic, rubber, they are insulators, and we know there are certain elements like silicon, germanium which are semiconductors. Metals, popularly example as conductors, wood, plastic, rubber as an insulator, and silicon, germanium which are used in electronics, semiconductors. Now, what is the difference between conductor, insulator and semiconductor scientifically? Scientific difference is based on their electrical conductivity value, that symbol is K, and it is given by 1 upon resistivity. You all as a physics student are aware resistivity as a unit of ohm meter. Therefore, electrical conductivity will have a unit of ohm inverse, meter inverse. If K ka value is very high, more than 10 to the power 4, then it is said to be a conductor. Right, the NCERT textbook gives a value from 10 to the power 4 to 10 to the power 7, but anyone greater than 10 to the power 4 is called as conductor. If the K value is between 10 to the power minus 20 to 10 to the power minus 10, lower value 10 to the power minus 20, higher value 10 to the power minus 10, that is very small. If very small electrical conductivity K value is existing, then such substances are called as insulator. Semiconductors have value of electrical conductivity K in a moderate range to 10 to the power minus 4 to 10 to the power plus 4, ohm inverse, meter inverse, then they are called as semiconductors. Right, we are all aware most of the metals, whether you say silver, gold, iron, copper, they are all conductors. Even ionic solids in molten condition are good conductors. Insulators, that immediately comes to our mind: wood, plastic, rubber. Okay, right, most of them are non-metals and most of them are molecular solids with no free electrons. They are insulator. Then metalloid like silicon, germanium are example of semiconductors. So, the entire learning process of conductor, insulator and semiconductor classification scientifically is based on electrical conductivity symbol K, which is given by the formula 1 upon resistivity. Then what is the difference between a metallic conductor and an electrolytic conductor? Now, right, immediately if you say, right, conduction is due to free electron, then you should know it is a metallic conductor. It is due to free electrons, where electrons go from negative terminal to positive terminal. Free electrons are responsible for metallic conductivity, while conductivity due to free ions is called as electrolytic conductivity. So, free ions are responsible for electrical conductivity. Example that you are able to see is aqueous sodium chloride, where sodium ions are moving toward cathode and chloride ions are moving towards anode, that is a positive electrode. And here the examples are metals like silver, gold, copper and so on. Now, entire concept of electrical conductivity is based on band theory. What is the band theory? Band theory is based on free electrons concepts, and in this atomic orbitals of metal come together to become molecular orbitals. So, according to this band theory, which is actually a hypothetical, it is a theory proposed by us to understand conductivity. So, in this band theory, assumption is atomic orbital come together to become molecular orbitals, and this molecular orbitals, many molecular orbitals of various atoms or cluster of atoms. So, molecular orbitals of many cluster of atoms give rise to a band, and this band, which is a cluster of molecular orbitals of various atoms, are of further two types. One is valence band and other is conduction band. Valence band is of atomic orbitals of inner valence shell. So, if you have a filled atomic orbital of inner valence shell, then they give rise to a molecular orbital, and accumulation of this molecular orbital is called as valence band. Conduction band. So, you can imagine this is a molecular orbital of inner valence shell of one atom. This is valence band of, or this is atomic orbital of inner valence shell of another atom, 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 and this gives rise to many atomic orbital of different energy, giving rise to a band called as valence band. While conduction band is of partially filled orbital, partially filled valence band or partially filled orbital or empty orbital called as conduction band. So, many atomic orbitals coming together, valence atomic orbital coming together give rise to a conduction band. Now, there is a schematic diagram. This has been shown for magnesium. If you are able to see, this all are very tightly held by the nucleus, while 3s electrons are not tightly held and they are responsible for valence band. Remember, in magnesium 3s orbital is filled and give rise to a valence band. Now, 3p orbital of magnesium is empty. That 3p orbital of magnesium, which is empty, give rise to a conduction band. And what you are able to realize in magnesium, valence band and conduction band are so close to each other that the electron from 3s can easily jump to 3b by absorbing heat energy of surrounding. So, the difference is very small. So, electron can easily go from filled valence band to an empty conduction band at any given moment of time, making magnesium electrical conductor. So, this was a schematic diagram to understand valence band and conduction band. Now, if you see conductors, insulators and semiconductors from perspective of band theory. Now, it is assumed that in conductor this is valence band, while this is conduction band. What you are able to realize, valence band and conduction band overlap with each other. Because valence band and conduction band overlap with each other, electron can easily move to conduction band. Moment the electron goes to conduction band, they are responsible for conduction of electricity. So, why conductors conduct electricity? Because in conductors valence band and conduction band overlap with each other. That is a small energy difference between them, or almost of the similar energy. Therefore, electron can easily move from valence band to conduction band. If you see insulator, the valence band and conduction band, that energy difference is very large. Such a large energy difference, the electron cannot move from valence band to conduction band even after providing larger amount of energy. So, even after providing larger amount of heat energy, electron cannot move. So, as per our logic, it is called as forbidden zone. Electron cannot go to conduction band ever. Therefore, insulator never conducts electricity, while in semiconductor the difference is very small. That is the reason while semiconductors are at low temperature are working as good as insulators, and at room temperature they behave like conductors, because the gap between them is very small. So, semiconductor, conductor and insulator as per band theory have a difference. In conductor they overlap. In insulator the difference is very large, cannot be achieved by even heat energy, while in semiconductor the gap is very small, can be easily achieved by heat energy. In this case you do not require heat energy, that means conductors will conduct electricity even at low temperature, even at room temperature. Now, if you come to semiconductors, we realize that in semiconductor the gap between the valence band, which is this one, and the conduction band, which is this one, the gap is very small, and that gap can be easily achieved by small amount of heat energy. So, electron can easily go from valence band to conduction band. That means semiconductor will start conducting electricity at room temperature or even on warming. But the number of electrons in semiconductor is found to be very small as compared to metals. So, if you want semiconductors to behave like a good conductor like metals, like silicon and germanium, which are semiconductor, and you want silicon germanium to behave like a conductor, then you should add a proper impurity like arsenic and boron. By adding proper impurity, we are going to increase the conduction, and such a phenomenon of adding a proper impurity to a semiconductor so that they become conducting very well is called as doping. So, addition of impurity to semiconductor by which its conductivity increases is called as doping. So, that was basic information about electrical properties. So, we come to the next part, semiconductors. We are aware as a semiconductors there is a very small difference between their conduction band and valence band, and therefore, electron can easily get excited from their valence band to conduction band by small amount of heat. So, most of the semiconductors by slight warming even at room temperature conducts electricity like silicon germanium. If you add a impurity, a proper impurity like arsenic or a boron to semiconductor like silicon germanium, then they have conduction increased and almost like conductors. When you add a proper impurity to semiconductor and make them as good conductor as normal conductors, then the process is called as doping. So, when you come to doping, then which elements are added for doping? First, you should know in this p block elements: boron, silicon, germanium, arsenic, antimony, tellurium and astatine. This all are example given as semiconductors in NCERT. For a chapter of solid state, we are going to look at only silicon and germanium as a good example of semiconductors. And group 13 and group 15 will be looked as impurity to be added. Silicon, germanium are very good example of semiconductors. Now, if you happen to add boron to silicon, germanium, then it is found that silicon germanium's electrical conductivity increases. Process doping, and such type of semiconductor is called as p type semiconductor. So, if you add group 13 to group 14, then such type of semiconductor is called as p type semiconductor. If you add group 15 element like arsenic, antimony to group 14 element, then our silicon germanium semiconductors are now called as n type semiconductor. If you check silicon, silicon is a network solid. You are aware silicon is a network solid like this. You should all also be aware that silicon bonds are not very strong. So, by providing some amount of heat, this bond breaks and the electrons become free to conduct electricity. So, if you heat, then silicon, which is made up of 4 electrons, then that 4 electrons become available, some of this 4 electron becomes available for conduction of electricity. Now, imagine in this network solid, if you add an impurity of arsenic, you know arsenic is group 15 element and it has how many valence electrons? It has 5 valence electrons. You are able to see silicon contributes 1 electron each to arsenic to form a covalent bond, and arsenic contributes 1 electron each also to contributing silicon, but 1 electron remains extra because it was made up of 5 electrons. Because of this free electron, now in the same arrangement of solid state, you have got 1 extra electron free for every arsenic atom which is added, and this free electron is responsible for conduction of electricity. Because conduction of electricity is due to that free electron, and you know free electron is dash charge, negatively charged, such type of semiconductor is called as n type semiconductor. That means, if you add group 15 to silicon, you will have n type semiconductor because of that extra electron which has come. That electron has what charge? Negative charge, because of that n type semiconductor. So, conduction is due to that electron. Now, if you go to the next one, silicon has 4 valence electrons, and if you happen to add a boron which has 3 electrons. So, now boron contributes only 1 electron each with every silicon, but are you able to see here silicon has contributed the electron, but boron is unable to contribute the electron. So, here the contribution due to boron to a silicon is not there. So, at one place there is no electron. So, we say there is a vacancy or there is a hole. So, for us this is nothing but a hole. This hole. Now, as soon as you apply potential difference, then what happens? This electron can come at this place in that hole when you apply a potential difference and fill up that space. But then there is a hole created at another silicon. Then, as you apply potential difference, then the other electron from the other silicon can come at that place. And what you are able to realize, there is still a movement of electron. Now, movement of electron still takes place. You know, movement of electron is nothing but electricity. So, you are able to see a flow of electricity, right? For one observer, scientifically it is a flow of electron only, but we feel along with flow of electron there is a flow of holes too. So, there is a flow of holes too. So, if you check, as if the hole is moving. So, electron goes from here and the hole comes up at the new place. Then electron again comes there and the hole has shifted its position. Again the hole has shifted its position. Are you understanding it? So, it feels as if the hole is responsible. Hole means a area with no electron. Area with no electron means positive charge. So, as if positive charge is responsible for conduction of electricity. Therefore, such type of semiconductor is called as p-type semiconductors. So, you realize that by adding group 15 to silicon, you got n-type semiconductor because of that one extra electron present in group 15, and group 13 element when added to silicon gave rise to p-type semiconductor because of that extra hole or positive charge. Therefore, it got the name as p-type semiconductors. Now, other than what we have learned silicon germanium as a semiconductor, in synthetic methods they have prepared more semiconductors like group 13 and group 15 elements. If they are mixed together, they are found to simulate group 14 only. Group 14 element 13 and 15, if you average it out, is it not group 14? And if you take 12 and 16 and if you average it out, is it not group 14 germanium and silicon? So, they simulate like group 14 elements of germanium and silicon. So, this group 13 and 15 alloy between indium and antimony is found to have semiconductor property. Aluminium phosphide or a compound of group 13 aluminium, group 15 phosphorus, aluminium phosphide is a name, also shows semiconductor property. Gallium arsenide, gallium group 13 element, arsenic group 15 element, they also show semiconductor property. Similarly, group 12, that is a transition element, last series or last group, and group 16 elements, that is p block, which is a block of oxygen, sulfur, selenium, tellurium, then zinc sulfide, zinc group 12, sulfur group 16, zinc sulfide shows semiconductor property. Cadmium sulfide group 12 cadmium, group 16 sulfur shows semiconductor property. Cadmium selenide again group 12, group 16 shows semiconductor property, and similarly mercury telluride also shows semiconductor properties. Unusual phenomenon also has been seen in the nature error. Tellurium oxide, not tellurium oxide, titanium oxide. Now, we know that when they form a compound, the C of electron found in metal is lost completely, and therefore, most of the compounds of metal do not conduct electricity. But it has been found tellurium oxide, which is a compound of a metal, still shows magnetic and electrical properties like metals. This unusual behavior can be accounted that there are certain C of electrons still remaining. Similarly, chromium 4 oxide, that is chromium oxidation state 4. So, chromium 4 oxide. Chromium 4 oxide is also found to have electrical properties like metal, although it is a compound. Rhenium trioxide, although it is a compound, shows electrical property like metal. This unusual behavior is still accounted to C of electrons, but still research is pending. Rhenium trioxide on the other hand is found to have very good electrical properties like copper. Then gallium arsenide or semiconductor is a new age semiconductor and is revolutionizing the entire electronics industry around. So, this slide tells you unusual information about semiconductors and some information about conductors, right, which we never expected at the first place they should be conductor. And rhenium trioxide is surprise for us, shows electrical conductivities like copper. So, we go to the next part, magnetic properties. Magnetic properties in solids is due to what? Spinning electrons. Each spinning electrons behave like a tiny magnets and creates a magnetic field around. If you see this diagram, you will realize electron spinning. The spinning electron. Do not see that red marker pen ink, just see about that spinning electron. The spinning electron produces magnetic field in a specific direction. So, that yellow color line has been shown as a magnetic field produced by that spinning electrons. Electron spins around itself and produces a magnetic field. Each electron which is spinning and also revolving around the nucleus produces a magnetic field. Many a times this electrons magnetic fields are arranged in such a manner that they almost cancel each other. So, many a times this magnetic fields cancel each other and the net magnetic field is found to be 0. What you are able to see is again a nucleus made up of a proton and neutron, and these are the 2 electrons of the first shell. They spin in different direction, that we are already aware of Pauli exclusion principle, and the net magnetic field for them is in such a direction that they cancel each other and net magnetic field is found to be 0. Now, in any case, if the electron spin is not cancelled, then if any one electron's magnetic field is not cancelled, spin is not cancelled, then it exhibits magnetism. But if every electron's magnetic spin is cancelled, then it shows no magnetic property. So, to show magnetism, the spin should be unbalanced, at least of one electron. Now, based on magnetic properties, substances are mainly of 3 main types. They are diamagnetic, paramagnetic and ferromagnetic. In diamagnetic, all the electrons are paired, that means their spins are cancelled, that means net magnetic field is 0. Then such substances do not get attracted towards magnet, on the other hand they get repelled. Many examples around us are diamagnetic in the nature. Nitrogen with total number of electrons paired, fluorine with all the electrons paired, NaCl with all the electrons paired, they are all found to be diamagnetic. What are paramagnetic substances? Some electron ka spin remains unbalanced or is not completely cancelled, then such substances are weakly attracted towards magnet or magnetic field. Example, O2, oxygen, which was explained as a paramagnetic in 11th standard under molecular orbital theory. Copper 2 plus with 3d9 is 1 electron non-cancelled. Fe3 plus also has 3d5 uncancelled electron. Similarly, chromium 3 plus also has some uncancelled unbalanced electron spins, therefore shows paramagnetic nature. Substances which contain large number of unpaired electrons are shown to be strongly attracted towards magnet, then such substances are called as ferromagnetic. In the world, number of ferromagnetic substances are very few, and in your syllabus you have only 5, and all these 5 examples have to be by hearted by the student. So, remember Ficoni, which are transition metals, gadolinium, lanthanide and CrO2. These are the 5 examples which are ferromagnetic, which are strongly attracted towards magnet, and they themselves also can be converted to magnet. You have to by heart this 5 examples of ferromagnetic substances. Now, if you see MnO, where Mn has oxidation state of +2, you know Mn has 3d5, 4s2. So, if you go to Mn plus 2, it has 3d5, and if you draw a box diagram for 3d5, you will find it has large number of unpaired electron. When it is large number of unpaired electron is expected to be highly ferromagnetic, but was found to be diamagnetic. Now, for us this is a surprise. We expect to have so many number of unpaired electrons, and we expect it to be ferromagnetic. What was observed in the nature was diamagnetic. What is the reason? So, reason is given by a concept of domains. Now, what is a domain? Domain is cluster of various atoms with a similar type of spins. These are different atoms which spins in same direction. Well, this is another domain with electrons having spins in same direction. This is another domain with different direction spins. So, this is domain 1, domain 2, domain 3. Every atom has a net magnetic field, but all these atoms have net magnetic field in one direction. So, all these magnetic fields are considered to be one cluster, and that cluster is known as domain. While this is considered to be another domain, because all these magnetic spins and directions are different, and this is another domain, domain 3. Are you understanding it? There can be many domains. Now, we come to a concept of domains. Only domain concept can help us understand further types of magnetic properties. So, magnetic substances are a further 3 types based on domain concepts. So, we use domain concept to understand that. Here, all the electrons are unpaired, or there are many electrons unpaired. Many electrons unpaired. When many electrons are unpaired, they are expected to be ferromagnetic, and observation is also ferromagnetic. Such substances are called as ferromagnetic substances. This 5 example I said it before also, you have to by heart. Faerie magnetic substances also have large number of unpaired electrons. So, what is expected from them? Ferromagnetic, but what was observed from them? Paramagnetic. What do you mean by they are expected from them ferromagnetic and observed paramagnetic? Or expected large magnetic moment, they can be converted to magnet. This was what was expected, but was observed was they were weakly attracted towards magnet, and they cannot be converted to magnet. Such substances are called as Faerie magnetic. You can remember the word Faerie. Faerie means less. Example is this magnetite. Fe3O4 is called as magnetite, and this are popularly called as ferrites. So, magnetite and ferrites are Faerie magnetic substances. This also contains large number of unpaired electrons. So, what is expected from them? Ferromagnetic. What is observed? Unusual diamagnetic, and example is MnO. Now, why like this? In this, all domains or major domains are in one direction. When major domains or all the domains are in one direction, it will have large magnetic properties and will be ferromagnetic. If domains, one domain and another domain cancel, one domain, another domain cancel, one domain, another domain cancel, then all the domains are cancelled. So, net magnetic field on a whole is diamagnetism. If certain domains only cancel and net magnetic field exists, only certain domains are cancelled, then such substances are paramagnetic, and as a whole the substances are called as Faerie magnetism. So, this entire concept is explained by domains, which will be again taken in physics under the chapter of magnetism. If you want to see a domain diagram, these are domain diagrams. Remember, it is not a d orbital, it is not a p orbital, it has been shown as domains. This all domains are in same direction. That means such a substance is ferromagnetic. Example, iron, cobalt, nickel, gadolinium, CrO2. What you are able to realize? Domains are cancelling each other. Right? If domains are cancelling each other, then substances are anti-ferromagnetic as per NCERT. There is only one example. In Faerie magnetism, remember Faerie magnetism, right? There is certain cancellation, and net there is overall net is present. Such substances are called as Faerie magnetism. Example, Fe3O4, ZnFe2O4, MgFe2O4, those are examples of Faerie magnetic. In paramagnetism also there are few unpaired electrons, while in all this there are large number of unpaired electrons, while this has few number of unpaired electrons. Paramagnetic, example oxygen, copper 2 plus, chromium 3 plus, Fe 3 plus, they are example of paramagnetic substances. How to identify magnetic nature as a student for our MCQ purpose? By heart ferromagnetic substances, by heart anti-ferromagnetic substance of syllabus. Only one example is there, MNO. By heart Faerie Magnetic Substances of our syllabus, Fe3O4, and you remember ferrites ZnFe2O4, MgFe2O4. These are examples of Faerie magnetic substances. By heart this 5 example, as per NCERT by heart only 1, then by heart this example, they are all Faerie magnetic substances. After you by hearted as step number 1, go to step number 2. Remaining all substances are other than ferromagnetic. Other than ferromagnetic, that means they can be either dia or they can be paramagnetic substances. Under that, first category, molecular species or polyatomic species. When I say molecular species or polyatomic species, that means they are made up of 2 or more atoms. In this case, count total number of electrons. If total number of electrons is odd, they are paramagnetic. If total number of electrons are even, then they are diamagnetic. Example is B2O2 and S2, where B2 has 10 electrons, S2 has 16, and sulfur 2 has 32 electrons. So remember, B2O2 and S2 are paramagnetic. Remaining all substances are diamagnetic. I say it again. You should first check whether it is a polymolecular species made up of 2 or more atoms. If it is made up of 2 or more atoms like H2 minus, N2 plus, then count total number of electrons. If total number of electrons are odd, then it is definitely paramagnetic. Example H2 minus, total number of electrons are 3. So it is definitely paramagnetic. N2 plus, total number of electrons are 13. That means it is definitely paramagnetic. But if total number of electrons like H2O is 10, then it is diamagnetic. If you see carbon monoxide made up of 6 plus 8, 14 electrons, then it is definitely paramagnetic, because total number of electrons are even, and for even number of electrons to be paramagnetic, there are only 3 examples which are unusual, explained by molecular orbital theory, B2O2 and S2. Now, if you are dealing with monoatomic species made up of only one atom, they can be atom or an ion, then write electronic configuration. While writing electronic configuration, if they have one or more unpaired electron, then they are paramagnetic. If they have no unpaired electron, then they are diamagnetic. We don't have any exception case in this case. So they are all diamagnetic. If you check water, total, water first thing, it is polyatomic species. If it is a polyatomic species, count total number of electron. If you count total number of electron, it is 10. Total number of electrons are even, therefore it is diamagnetic. Here in this case, count total number of electron. Nitrogen has 7, hydrogen has 4, minus 1 because it has lost 1 electron due to positive charge. Total number of electrons are even because it is polyatomic species, therefore it is dash in nature, diamagnetic. Similarly, this is also a polyatomic species, and if you count total number of electron, it is even, therefore diamagnetic. If you see another example, Cl plus, it is a monoatomic species. If it is a monoatomic species, then write down its electronic configuration as per this rule. If you write down electronic configuration, it has how many electrons? 16 electrons. 1s2, 2s2, 2p6, 3s2, 3p4. 3p4, that means it has unpaired electron, therefore it is dash in nature. paramagnetic in the nature. What you should have realized, if it is a monatomic species, write electronic configuration. If it is a polyatomic species, just simply count total number of electrons and you will be able to decide whether the substance is diamagnetic or paramagnetic in the nature. So, we come to the discussion of this chapter called as solid state. So, that was all the discussion related to theory of this chapter, solid state. Thank you all.